Alright, hello everyone. In today's video, we are going to be going over a flash calculation for this tank over here. And pretty much all a flash calculation is that we have a binary mixture coming into our tank right here. In this case, we're going to be doing a benzene and toluene again like we did in our last video. So that is going to be coming in, and in this tank, we are going to have a constant temperature and pressure, alright? So we are going to know the temperature and pressure, and it's not going to be changing, and it's going to go into this tank, and it's going to separate out into the liquid phase and the vapor phase, all right? And pretty much what we're going to be trying to find out is we're going to be trying to figure out the composition of the vapor going out and the composition of the liquid going out, as well as the total amount going into the vapor phase and liquid phase over here, all right? And it's important to know that if you think back to our last video when we were calculating the dew pressure and the bubble temperature, all right, we had our graph going here, and then this was our pressure right here, and this was our xi and our yi right here, right? We had it going up like this and then over like this, and this was at a constant temperature, all right? This is any selected temperature you want, all right? And for our flash calculation right here, it's important to know that the pressure is going to be somewhere within this little twofold diagram right here. It's going to be somewhere within that. And yeah, that's important to know, all right? That means that we're going to have both vapor and liquid within this chart right here. And so now we are going to go ahead and get to solving this, all right? And so the first thing that we're going to want to realize is that the flow coming in is going to be equal to the flow of the vapor going out and the flow of the liquid going out. So we're going to write T is equal to V plus L. All right, that's simple enough. And we can also multiply this by the mole composition. All right, so we're gonna say that the mole composition going out is gonna be Zi. So we're gonna get T times Zi is gonna be equal to V times Yi plus L times Xi, right? Because if you remember in the last video, we used Xi to represent the mole composition in the liquid phase, and Yi to represent the mole composition going into the vapor phase. And all Zi is going to represent right here, that is just going to represent the mole composition over here when it is going into our flow chart. All right, and now we are going to use the equation that we used in our last video. That was Yi times the pure pressure vapor saturation. That is equal to the mole composition in the liquid phase times the total pressure over here. All right, and basically from there, I think we actually got these flipped around. I think it's supposed to be Xi over here and Yi over here. I think that's how it's supposed to be. And pretty much what we can do from here is that we can go ahead and divide these mole compositions to get a coefficient that is going to be represented by Ki. And basically what Ki is going to be is it's just going to be this Xi over this, or the Yi over the Xi over here. So we're going to go Ki is equal to Yi over Xi, right? And we know if we have Yi over Xi, we can go ahead and set that equal to the pure pressure vapor saturation divided by the total pressure. So that's going to be Pi sat over the pressure, right? And we are going to know pressure, right? Because the pressure and temperature within this are going to be constant, and we're going to be given those at the start of the problem before we even do anything. So we're going to know this right here. And since we know the temperature, we can go ahead and we can solve for the pressure saturation right there. All right, so we are going to know both of these, which means that we can in fact solve for Ki. So that is going to be known to us, and we can easily solve for that. All right, now we are going to go ahead and derive the Rachford-Rice equation so that we can go ahead and solve for some of the unknowns that we are going to be looking for. And before we do that, we're going to go ahead and write down what it is exactly we are looking for, all right? So if you remember, we wanted to solve for the total amount that is going to be coming out in the vapor phase and the total amount of moles that's going to be coming out in the liquid phase. And then from there, we're going to want to know what the composition of that amount is going to be. So we're going to want to solve for xi and yi as well. And these are going to be our four unknowns right here. This is what we're going to want to solve and gain out of doing all this equation. And we're going to go ahead and hop into the derivation now. So the first step that we're going to do is we're going to know that the sum of the composition in the gas phase over here, and that's going to be subtracted from the sum in the liquid phase, and we know that is going to be equal to 0, right? We know this because the sum of the compositions are both going to be equal to 1, right? You're never going to have more than 100% of moles in the liquid phase or more than 100% in the gas phase. So we know that this is going to be equal to 1 always, and this is going to be equal to 1 always. So this is pretty much just saying that 1 minus 1 is equal to 0, right? And that makes sense. And basically what we can go ahead and do now is we can write this under one sum function. So we know that the sum of yi minus xi is going to be equal to 0, right? And from here, we could do this for any number of components that would be within the mixture. We don't have to just do it for this binary mixture. That is what we're going to be doing in this case, but we could have a mixture with as many components as we wanted. And we are going to start at I equals 1, because again, that is going to be our most volatile part of the mixture. So we're going to go from I equals 1 to 2 in this case, but again, you could go from any number of compounds. And from here, we're going to do a basic substitution. If you take a look over here, we can see we have two unknowns right here. So we're going to want to do a substitution so we can get less unknowns within this. And to do that, we're going to go ahead and set yi is going to be equal to ki times xi. We're going to go ahead and bring the xi over, and we're going to get this equation in terms of xi. So we're going to get the sum of ki xi minus xi, and that would be equal to, of course, 0. And then we can go ahead and factor out this xi right here. So that's going to be xi ki minus 1, like so. Alright, and now we need to go ahead and what we're going to want to do is we're going to want to come up with an expression that we can substitute in here for xi, because again, that is an unknown right there, and we're going to need to try and get that out of there. Alright, to get our substitution in for xi over here, we are going to go ahead and use this equation that we have up here. And as you can see, this one has yi as well, so we can go ahead and once again multiply this xi over and substitute xi ki in for that yi. So we are going to go tzI is equal to ki xi times v plus Lxi. And right here, this L is another unknown. We do not know the amount of liquid that is going to be coming out of our system. So we can go ahead and make another substitution in for that. And we can go ahead and do a t minus v over here, subtract v from both sides to get L by itself. So we'll go tzI is equal to ki xi v plus t minus v xi, and then we can go ahead and do a substitution, or a factor, excuse me, get this xi out in front. So we'll go tzI equals xi kiv plus t minus v. There we go. And now we can go ahead and divide this over by both sides to get the xi by itself. We'll go ahead and factor this v from the ki and make this ki minus 1. That's going to make our lives a little bit easier. That's going to be all over plus t. And now, just to make this a little bit prettier, what we can go ahead and do is multiply both sides by 1 over t. Right? And we're going to go ahead and bring this on over here. And what that is going to give us is xi is equal to zi over v over t, ki minus 1, plus 1, since those t's are going to cancel out. And here we go. This is going to be our expression that we're going to use for xi over there. Alright, now that we have our xi, we can go ahead and substitute that back into our sum over here. So we can go sum, and then zi ki minus 1. That is going to be multiplied by vt ki minus 1 plus 1. And that is all going to be equal to 0 over here. And once again, we are going to be starting at 1. Our I is going to be equal to 1. And since this is going to be a binary mixture, we're going to go to 2. And yeah, this is what we're going to be doing in our Python code later. That is going to give us our v over here. That is our one unknown we are going to be solving for. And once we have our v, we can go ahead and put that into this equation. And we are going to be given t, all right? That's going to be the total amount going in to our flash cylinder. And we can do some basic subtraction and get our liquid phase going out, the total amount of liquid going out. And once we have V and L, we can go ahead and come down to this equation right here and get the mole fractions. That's going to give us our yi and our xi. And that's how we're going to be solving for all 4 of our unknowns, that being the total amount of vapor going out, the total amount of liquid going out, and then the mole compositions of both of those. And yeah, we're going to go ahead and get into Python and get to writing those functions, and yeah, we'll get to that now. Alright, so now we are going to go ahead and perform our flash calculation in Python. I've gone ahead and written out this Rachford-Rice equation that we derived earlier in the video so that we don't forget any of it and get it all written out right. And for this flash calculation, once again, we are going to have the temperature and pressure given to us. It's going to be constant, so we're not going to have to do any calculations for that. And the temperature is once again going to be 393 degrees. And the pressure is going to be 150,000 pascals, so that's going to be 150 e to the third. And then the next thing we're going to want to do is we are going to need to know what the flow rate going into our flash tank is going to be, and we are given that in this problem. It's going to be 10 moles per second, and in our earlier video, when we were on the whiteboard, we represented it as t, so we'll go ahead and give that a lowercase t. That is going to represent the total flow rate going in, which is once again 10 moles per second. And then the next thing we're going to need to do is we're going to need to set up an array that is going to represent the mole fractions of our benzene and toluene. So what percentage of that flow rate going in is benzene and what percentage is toluene? And for that, we are given that it is 4 moles per second benzene going in and 6 moles per second toluene going in. Alright, so we're going to call this array Z, and we're going to go np.array. And then it is going to be 0.4 and then 0.6. Because, you know, obviously 4 over 10 is going to be 0.4, and then 6 over 10 is going to be 0.6. There we go. And then the next thing we're going to know is our k value that we came up with earlier to represent our yi over our xi. We also said that that was equal to the pure vapor pressure at a select temperature over the total pressure. So we know that K is going to be equal to P dot P vap at the given temperature, and we are already given that. We know it's going to be 393 degrees Kelvin, so that's going to be no issue for us. And then we also can divide that by P, and since we're already given the pressure, this is going to be no issue for us. We know both of these, so K is going to be easily calculated, and that's going to be no issue. Alright, and now we're going to go ahead and get into writing our functions. We are going to call this the Rachford-Rice, so we'll go RR, and then put the variable V in there, and then we'll just call it something random like E, V0, and what we're going to want to return for this is we are going to want to return the sum of our Rachford-Rice equation over here. So we'll go ahead and copy and paste this on down. And instead of using this V over T, that should be a V over T right there. That should not be a V minus T. We're going to go ahead and write out an E for that just to make our lives easier. This is actually what we're going to be solving for, is this E value right here. Alright, let's just make sure all of our parentheses are matching up. We'll go ahead and get some around here. Alright, that's looking good. I think that's all we need from that right there. Alright, and then once again, our E is going to be equal to the Rachford-Rice, and we have to go ahead and give that a guess, so we'll go 0.8, and then we'll do .x 0, so we can get the first value within this array that it's going to create, and then we'll shift enter, see how that's looking. Invalid syntax. Not sure what's wrong with that. Well, guess we'll just go ahead and call it 150,000. Oh, we didn't include the equal sign. That was the issue. Alright, tuple. Alright, so we did make a few mistakes over here. The first one being is that we are going to need to sum this. So we're going to go mp.sum and then get some parentheses going all the way outside. And then we're going to need to include brackets because this is going to be creating an array for us. And then the next thing we're going to do is we do need to include that root function over here, like so. And there we go. We'll run that to make sure she's working for us. Alright, that is working nice and dandy for us. Alright, so the next thing we're going to want to do is we currently have this solved for E, which is not what we want. This is representing the V over T that we have, and we just wanted to get the flow rate of the vapor going out of it. So we're going to need to multiply this by T, which is the total, to get the V that we want. So we are going to go V is equal to E times T, like so. Alright, and then if you remember from our whiteboard, we also said that the total flow rate going in is going to be equal to the vapor flow rate plus the liquid flow rate. So we know that the liquid flow rate is going to be equal to T minus V. So that is going to give us our liquid flow rate and our vapor flow rate. And now all that's left to do is we need to find the mole composition of these. So we have the total amount. Now we just need to know what percentages are going out. All right, and to get that, we are going to go x is going to be equal to, it was similar, we did a derivation for x earlier in the video on the whiteboard. It was very similar to what we had right here, so we'll go ahead and copy and paste that on down. And it was pretty much the same thing, except we did not need this k minus 1 here. I believe it was just the z over this e value times k1 plus 1. There we go. Alright, we'll run that, make sure it's running alright. Invalid, alright, don't need that there. Alright, and then to solve for our y down here, we're going to once again use that k function that we found earlier, which was that k is equal to the y over x. So we're going to say that y is equal to k times x, and then we're going to shift enter that, and then we'll go ahead and run this and make sure that everything is working the way that it should. So hopefully this will give us all the right answers. I guess we'll go ahead and run that one at a time. That's not what we're looking for. We'll go V. Alright, and L. And X. And Y. Alright, here we go. So basically what this is saying right here is that when we have a temperature of 393 degrees Kelvin and a pressure of 150,000 pascals, we are going to get a flow rate of about 24.86 moles per second going out into the vapor phase and negative 14.86 moles per second going out in the liquid phase. And the composition of the vapor phase is going to be 0.115 moles benzene, and the other is going to be 0.84 moles toluene. That is going to be the mole fractions right there. And then this is going to be the mole fractions for the gas phase down here. And if we really think about that, it's not really going to make a whole lot of sense. The most this could be is 10 moles per second, right? Because we cannot have more than 10. If we have 10 going in, we can't have 24 going out. And this can't be negative. The most this could be is 10 and 0. And the reason it is doing this is because, once again, if we look up here at our diagrams that we made earlier for the boiling point and the dew points, we can see here, let's take a look at this pressure graph, for example. We have 0.4 moles of our benzene, which is the one that we graphed over here on our x-axis, and we have 0.4, and at the pressure that we have for this, it's going to be 150,000. So if we go to 0.4 and 150, that is going to be about right here, which is not in between our envelope right here. So that means that it's not going to work properly. In order for this flash calculation to work properly, you are going to have to pick a point that is within one of these diagrams. And if we go over here and take a look at the temperature graph, once again we have 0.4 and 393 degrees Kelvin, and that is going to be about right here. So that is once again outside of the envelope, which means that this calculation is not going to work, alright? But if we wanted to fix that, we could go ahead and either raise the pressure or lower the temperature. So we'll go ahead and do that. So at 0.4 miles, it looks like it would work at 385 degrees. So we'll go ahead and drop the T down to 385. And then that should make this all work out for us. Yeah, it's looking much better. As you can see, we have about 3.8 moles per second going out into the vapor phase and 6.2 moles per second going out into the liquid phase. That is what you want to see. They both add up to 10, and neither of them are less than 0 or more than 10. That's exactly what you want. But as you can see here, it's not exactly the best separation right here, as the moles going out into the vapor phase is going to be 0.526 moles benzene and 0.47 moles toluene. That's not exactly the kind of separation you want. You want to see one of these closer to 0 and 100. You're not going to want to see it close to a 50-50. So you would have to pick a different temperature and pressure if you wanted to see a better separation. But yeah, that is how you do it. These are the functions you would use to write out a flash calculation. And as long as you're picking temperatures and pressures that are within this specific envelope, depending on your percent moles of benzene going in, then this should all work well. And yeah, that is going to be it for today's video. I hope you have a good one. And yeah, make sure to smash like and subscribe, and also leave a comment.